first order ordinary differential equations, dy over dx, so first derivative, that's why first order, equals some function of x and y, where y is dependent variable and x is independent variable. Y depends on x. Separable equations. If this function f xy can be written as, let's say, if fxy is a product of two functions, just let's say f1 pure function of x alone times second function f2 just pure y. Okay, this is a function of x alone and this is a function of y alone. If we can write this function f as a product of two individual functions, then in that case we call this first order differential equation, then one is called separable, because we can separate the variables. In this case, equation 1 becomes dy over dx equals, this is a product, so f1 x times f2 y. Now we can rewrite this equation with the help of differential form, which is same as cross multiplying. So let's bring f2y to the left side, so that will be times, so 1 over f2y dy, move dx, so f1x dx. Now in the left side we have a function of y and dy, in the right hand side we have function of x and dx. Now integrate, okay, integrate both sides, and if possible solve for y, and that will be the answer, that will be the solution of this ordinary differential equation. Integrate and solve for y if possible. If we cannot solve for y, we still have the solution in implicit form. Okay, let's do an example. Example 1, solve dy over dx equals xy, comma y is bigger than 0. Okay, let's solve this differential equation. In the right hand side is a product of x and y, and this is separable. Now let's separate the variables. Bring y to the left side, so y, it will be 1 over y dy equals x dx. And by the way, we can divide by y because y is not 0, it's given. Now integrate, so we get 1 over y dy in the left hand side and x dx in the right hand side. And antiderivative of 1 over y is natural log of absolute y, but y is positive, so we don't need absolute value, is equal to antiderivative of x is half x squared plus integration of constant. Okay, integrating constant, this constant of integration c. Now it looks like we can solve for y, so let's exponentiate both sides. Exponentiate both sides, that means e raised to left hand side is equal to e raised to right hand side, that gives e in natural log, their actions cancel, so y equals e raised to that plus e raised to c. And by the way, whenever we have x raised to a plus b, this is same as x raised to a times x raised to b. So we can write in this way, e raised to c first times e raised to 1/2 x squared. That is same as, this is the answer, but we can do better. Y is e raised to c, c is a constant, arbitrary constant, so e raised to c is another constant. If we say, let's say c1, then e raised to c1 is another constant. Let's write c times e raised to 1/2 x squared. That's final. Okay, let's do another example. Solve dy over dx is equal to x times cosine square y. This is separable because the right hand side is a product of a pure function of x and a pure function of y. Let's bring y to the left side. It's times, so divide by cosine square y, 1 over cosine square y dy in the left hand side. Move dx to the other side, so x dx. Then integrate both sides. Okay, at the same time 1 over cosine squared, we don't know the antiderivative of 1 over cosine squared, but reciprocal of cosine is secant. As we know, 1 over cosine theta is secant theta. That means 1 over cosine square is secant square. So we can rewrite 1 over cosine square as secant square y dy. How does this help? Because antiderivative of secant square is tangent. Okay, that's in the left hand side is equal to antiderivative of x dx in the right hand side. Let me go down. Now antiderivative of secant square is just tangent, in this case y, tangent y is equal to, again antiderivative of x is half x squared plus c. And finally we can solve for y as a tangent. Take tangent inverse both sides, then y will be tangent inverse of half x squared plus c final.